In this video, we'll be looking a little bit more into binary and more specifically, mostly error detection and correction. So we chose binary in the first place because of that it was the system that sort of maximized our tolerance to fluctuations, to noise out in the world. So we had some like a finite physical thing like a voltage or a current, and we wanted it to represent something. And we decided discrete was better than continuous. And then we decided that within the discrete binary was the best. It gave us the largest regions, um, and so therefore the most tolerance. But still, errors are going to happen, and we'd like to be able to detect when that happened. So we really break our physical region down into two regions. One sort of we break our physical region down into three regions, a sort of like a high and a low and an intermediate that we'll say doesn't represent a number. And so then the errors, binary error, then can sort of come into two categories. One being that it's in this no man's land that's not interpreted. And so if you see a voltage, a current, what have you, that is not interpreted, you know that some error occurred. And then the other one is a bit flip, so that something that should have been zero became one and vice versa. Okay, and we'll be mainly talking about this sort of bit flip problem. Okay, so we're going to look at sort of things you can do with binary strings. Sometimes I'll call them numbers. They don't necessarily have to really be representing a number, but some binary string. And we're going to look into ways with binary strings that we can determine, and it's usually by adding extra bits to what we are storing, transmitting, what have you. But with these extra bits, we can determine if an error occurred. And sometimes with a little more elaborate schemes, sometimes we can correct that error, at least under certain assumptions. Okay. So sort of at the sort of lowest level, you are sending little blocks of information. And we want to have schemes that have built in this idea of knowing whether or not an error has occurred. So this is not detecting the error, but most of our basic transmission schemes have error detection sort of built in. So even at the lowest level of sort of the keyboard sending like a byte of information or something, there is some kind of uh, error detection going on. So one thing we know is that sort of built into one of our most primitive sort of representations of 8-bit strings ASCII. We have special um, bit combinations within ASCII that represent acknowledgement and non-acknowledgement. So some information is sent and from a source to a receiver, and then the receiver checks for errors and then will send an ACK if no errors are found, and an ACK if errors were found. And then in the simplest uh, transmission, then an error will lead to retransmission. And so we will see in different levels of sort of internet protocols, we will see checksums and CRC, cyclic redundancy checking, and sort of Depends on the protocol. We'll discuss a little bit sort of why that is. Okay, but here is the sort of the ASCII code, and we see there the special cases for ACK and NAC. So it's sort of built into some of our most primitive representations of error detection. And this is not detecting the error, but built into our system is ways to acknowledge that we got something without error, or we got something or we did detect an error. Okay. Another thing that comes up in when we talk about transmission and internet protocols is, and again, we're transmitting bits, many bits, but bits, is the bit error rate. And so this is some ratio of bits that have errors. So how many flipped bits do you see? And it's usually represented sort of um, as a sort of a negative power of 10. So then if you said that the BER was 10 to the minus 6, you mean that 1 out of 10 to the 6, 10 to the minus 6 is 1 divided by 10 to the 6. So 1 out of a million bits, one of them flipped. Okay. And this will be a measure because we need then when transmitting data to retransmit, the bit error rate will tell us how often we will need to retransmit data. So when we're trying to, as we always are, trying to do more faster, the bit error rate will give us an idea. As we go faster, we might make more mistakes, and then making more mistakes requires retransmission. And so then we need to sort of balance the speed so that we don't make too many errors, because the retransmission will then slow us down. And so the measurement is the BER, and then the device or procedure that can give you the BER is a BERT, bit error rate test or tester. Okay. I just want to emphasize that although I'm talking, when I just mentioned, I was talking about internet protocols having error detection and sort of like checksums and what have you. But um, anything sort of beyond the sort of processor dealing with memory uh, has really is transmission. So we have um, our basic our basic computer, our processor, control, memory, and basic I/O, and then anything outside of that, our hard drives or solid state drives, sort of anything else, the monitor and what have you. Those things usually are sort of a transmission protocol with some error detection built in. So transmission doesn't always mean outside the computer. It might be inside the computer. But in computer architecture, when we talk about the architecture, we really mean that sort of smallest functioning unit, and things like the hard drive. We think of a normal language as part of the computer, but in computer architecture, we might not be thinking of them as part of the computer. Okay. So we want schemes to know when an error occurred, and depending on what we're doing, we might want to fix it. So just to know, if we just want to know if an error occurred, that is error detection. And then if we want to fix it, that will be error correction. And so then in error detection, we will just say a mistake occurred, do it again. Error correction, we will try to find the offending bit or bits and flip them back to what they should have been. Okay. So one of the sort of simplest error detection schemes is known as parity. And so there's sort of two varieties of parity, even and odd. And so the first thing you have to do is sort of come to an agreement. If you are transmitting data um, with someone or some other, one device and another device, they have to come to an agreement ahead of time if they're going to use parity, and then if they are using parity, what type, even or odd, that they're going to do. And so we have, again, binary strings, sequences of zeros and ones. We will ignore the zeros. Effectively, we'll say count up the number of ones. Um, and if the number of ones is odd, let's say we're doing even parity. If the number of ones is odd, then we will add another one, the parity bit, and make it even. And if the number of ones in the data was even, we will make a parity bit of zero, and thus it will remain even. So we have our data, and then we have the extra bit, the parity bit. So all these error detection schemes involve sending additional bits. In parity, it's you have a small data size, maybe a byte, and you're sending one additional bit, the parity bit, and then we make some agreement on are we doing even or odd parity. You figure out for your data the what the parity bit should be. The source will figure out what the parity bit is, send the data along with the parity bit. Then the receiver will perform a parity detection and be looking for, in our example here, even number of ones. And if it doesn't find it, it will say something went wrong, send it again. Okay, so we know through, so there was an agreement ahead of time, there was the data, there was the additional error parity bit. The two systems, one system does some quote unquote calculation to figure out what parity bit should be sent. The receiver will do a parity check and we will detect that there was a mistake. We don't know which bit caused the problem, so it is detection, not correction. So again, we're just assuming even parity here, and you just sort of go across the data. So all those D's stand for data, and you count the ones. So in that first row, there were 3 ones. 3 is odd, so we would make the parity bit a 1. So then it would be between the data and the parity, 4 bits, and 4 is even. In the second row, there are 2 bits and 2 ones in the data, and 2 is even. So in order to keep it even, we would make the parity bit 0. This is the game. Okay. So now I'm saying that you sort of count the number of bits, but that's um, electronically, that's actually a little more complicated than needed. And what we really just need is what's called an excluded OR. So we need a multi-input excluded OR. So however many bits of data there are, that's how many inputs there are into the excluded OR, and then the excluded OR will determine what the parity bit should be. Then the receiver would have um, sort of an excluded OR with sort of one more input. Okay, so the simplest excluded OR truth table is 2 zeros give you 0, a 0 and a 1 in either way give you a 1, but 2 ones give you a 0. So this is parity for 2 bits. You see that in row 1 there were 0, 1, 0 was even, so the parity was 0. In rows 2 and 3 there was 1, 1, And in order to make it an even number of ones, we made the output, the parity bit, a one. And then the last one, the A and the B, the data inputs were both one. And we wanted a parity bit of zero to keep it even. And then if we have three inputs, you just have a three input excluded OR, and then you just keep going up. Now, excluded OR is, a fairly complicated circuit, but not as complicated as, say, actual counting. All right, so that's it for this one. We'll talk about other detection schemes in a later discussion, but this is our first error detection scheme, the parity bit.